Hi, so this is the course of Thursday, je vais y arriver, May 28th, and we are restarting on page 15 of the course about heat. Okay, I sent you on Classroom an extension of this course. I have added some more stuff and I've corrected some mistakes, rewritten the equations, etc. So when we mix substances, we have substances which the warm substances, they will lose temperature, they will lose energy, so their temperature will decrease. So we will have a delta T which is negative here, so we'll have a negative contribution to Q, and we have substances who increase their temperature, so they're going to have a positive Q. Okay, so these Qs, they can represent heat which is received or heat which is ceded or given, and we have an equilibrium equation which is this: the sum of the contributions is equal to 0. Now we have contributions which are a bit special. If we have a calorimeter, the calorimeter has a constant C which takes into account all its volume, all its mass. So the term for a calorimeter is C delta T, where C is the value of the calorimeter, and this is in joule per degrees, okay, since it's multiplied by degrees. And then we have another type of term which describes the state changes. So if you have a state that changes from solid to liquid, for instance, you need a lot of energy to do this change, okay? So you're going to have a term which is going to be M times the latent heat. And the latent heat, for instance, if you have a substance which is melting, it will be the latent heat for fusion. It's in joules per kilograms. And if you have a substance which is, instead of melting, which is solidifying, so the other way, is going to be M times Ls, where Ls is the solidification, the latent heat for solidification. And we have a relationship between these latent heats, which are just that one is the opposite of the other. Okay, so if you have a liquid here, a solid here, and the liquid here, if you want to go this way to melt the solid to make it a liquid, you need to give it an energy MLF. And if you go the other way, if you have a liquid and you let it freeze inside a medium which is colder, this substance will give you energy. Okay, so the L which characterizes that is the opposite of the other one. Okay, that was more or less a very bad resume of what we did. Okay, and now we have to solve this exercise. We put in contact 1 kilo of water at 10 degrees and 1 kilo of ice at minus 10 degrees. What is the equilibrium temperature and how much water and ice will we have at equilibrium? Did you try to do it? No. Hello? Are you there? Talk to me. Yeah. Be a bit more, I need to feel that there is somebody on the other side. Okay? So how do we solve this problem? First of all, what I would advise you to do every time you have to solve this kind of problem is to start with a diagram which is describing the evolution of temperature as a function of time. I recall you that temperature is capital T and time is small t. Okay, and if you do that, what should you draw? Well, you have 1 kilo of water at 10 degrees. So in some place we will need to have 10 degrees on the temperature scale. And we have ice at minus 10 degrees. So at some point we will need to have minus 10 degrees. And so the 0 degrees will be in the middle. Okay, so we start here. We have a certain quantity of ice at minus 10 degrees. This ice is going to do what? It's going to increase its temperature until it reaches 0 degrees. And then what happens at 0 degrees? Hmm? Hello, hello. You're not going to be silent like that for 1 hour, please, please. What happens when the ice reaches 0 degrees? Okay, there happens a plateau. Okay, so for a certain time, for a certain duration, the duration which is necessary for you to give enough energy, the the temperature is not going to change because now you have the phase which is changing. You're going from a solid phase here to a liquid phase here. Okay, and then if you continue to heat up the water, it will increase in temperature again. Okay, so I did this drawing, but actually what do we have? We have ice at minus 10 degrees, which is going to warm up, and we have water at 10 degrees, which is going to cool down, okay? And this process is going to stop somewhere, probably along the plateau, and this will determine how much of the ice has been melted and how much of the ice is still in solid form. Because along this plateau, what you have? Here you have a block of ice, which is at minus 10 degrees, okay? Ice is not necessarily at zero. Ice can be at minus 10, minus 20, minus 100 degrees. There's no, I mean, it can even be lower than that, okay? So you have a piece of ice. So when this ice is heating up, it arrives here, and here you still have your piece of ice, but this is now ice at 0 degrees. And what happens along this plateau? Well, what happens is that progressively the ice melts so that at the end of the plateau, this ice is now liquid. Okay? And what do we have in the middle of the plateau? Well, in the middle of the plateau, we have some ice which is still there and some water which is already formed. We have a mix. Okay, and the quantity of ice that is transformed into water is proportional to the length of this line. So at the beginning you have only ice, at the end you have water. In the middle of the plateau you will have half ice, half water, and at 1/3 of the plateau you will have 1/3 of water, 2/3 of ice, etc. Okay, the ice melts progressively, and then here you have water, so if you heat it up it becomes hot water. Okay, so as I told you when we did the exercises the other time, you should separate these different contributions because they require different computations. Okay, here in this phase 1 we will call 1, 2 and 3 the different phases. In this phase 1 here you have a Q1, which is going to be of which form? It's the usual term for heating up a substance. And don't do as if you didn't know. You know, this is M times C times delta T, and this is the mass of ice, and this is the sea of ice. Okay, be careful, the sea of ice is not the same as the sea of water. Okay. Here for 3, what do we have? We have a quantity of energy Q3, which is given to us by the water, which is going to cool down, because of course the ice is going to warm up and the water is going to cool down. Okay, so this Q3 is what? It's the mass of the water times the C of the water times delta T. Okay, and what I would like to do now is to compute this Q1 and Q3 to have a kind of understanding of where we will stand at the end. What will happen is that the water, when it cools down, it will give us energy. A part of this energy will be used to warm up the ice, and the remaining energy will then be used to melt the ice up to a certain point. That's how we are going to solve this problem. Okay? Good. Ael, besides you, there are other people who are listening? How many people are we online? Whatever. Okay. Good. Okay. So now let's compute how much energy the water gives us. Okay? Well, we know the energy which we get from the warm water, well, warm, it's 10 degrees, but it's still warmer than the ice. This warm water will give us a quantity of energy which we call Q3, and this is the mass of water times the C of water times delta T. What is delta T? The final temperature is 0 degrees, and the initial temperature was plus 10. Okay, so this quantity of energy is going to be negative because this is energy we get from the system. And now let's put in the real data. We have 1 kilo of water at 10 degrees, so this is 1. The C of water is 4,180 times 10 times minus 10. This is going to be minus 41,800 joules. Okay, this is the energy that we are getting from the water. Okay, now let's compute the term Q1. Okay, Q1, it's the mass of ice times the C of ice times the final temperature of ice, which is 0 degrees, minus the initial temperature of ice. And be very careful here. The initial temperature is minus 10, so it's minus 10, it's plus 10. Okay? How much ice do we have? We have 1 kilo of ice. What is the C of ice? Do you know the C of ice? Okay, where do you find the C of ice? You find it in the CRM table. Okay, here I'm not on the right page. Okay, but of course, ice is not a different substance. Ice as a substance is water. So we need to look under water. Okay, and underwater, you have here the specific heat, chaleur massique, and you see that this specific heat is given for the solid phase and for the liquid phase. Sometimes it's given for the vapor phase, but not always. So the value for liquid water is 4,180, but the value for solid water, for ice, is 2,060 joules per kilo per degree. Okay, so be very careful not to take the same value. Okay, this has to be the value for ice, and now it's times minus 10, so plus 10. This is 20,600 joules. Okay, so you see that we get, who's screaming? We get, I don't know, I hear somebody crying or screaming, I don't know. So we get 41,800 joules from the water. We use 20,600 joules to warm up the ice. Okay, so we are left with, well, we are left with 41,800 joules minus 20,600 joules. And this you can compute. And how much is that? Where the hell did I put my phone? Well, I can also do it by hand. It's 21,200 joules that are left in order to melt the ice. Okay, we are left with some Q to melt the ice. Okay, but how much ice do we melt with that? How would you do that? It's not very complicated reasoning. How much ice could we melt with 21,500 joules? Well, we need to know how much joules we need to melt all the ice, and then we see what percentage we have of this energy. Okay, so how much Q to melt all the ice? Okay, so you can compute it. The quantity of heat that you need to melt all the ice is given by what? Can you tell me, or you want me to tell you? So it's the mass of ice times the latent heat for fusion of the ice, of water. Okay? The mass of ice is 1 kilo, and the latent heat, well, we have to look for it. So we take the table again, and you see you have chaleur massique here, and here you have chaleur latente, latent heat. And you have latent heat for fusion, LF, and latent heat for vaporization. I recall you that if instead of doing fusion, you do solidification, you take minus the value of LF. And here, if instead of vaporization, which means transforming a liquid into gas, you do condensation, which means transforming a gas into a liquid, then the latent heat for condensation is minus the latent heat for vaporization. Okay? Here we want to melt the ice, so we need to take the latent heat for fusion, and the latent heat for fusion for the water is given here. 3.3 times 10 to the 5. You see, it's a very big value. Okay, it takes a lot of energy to transform a liquid into a solid into a liquid, or a liquid into a gas. Okay, it takes a lot of energy, much more than to heat up the thing. Okay, so we said the mass of ice is 1, the latent heat of fusion is 330,000 joules. Okay, and 1 times 330,000 is approximately 330,000. Okay, so now you can do a proportionality argument. You can say, okay, to melt all the ice, I would need 330,000 joules, but I have only 21,200 joules to do the job. So I will melt a percentage of the ice, which corresponds to this divided by this. Okay? You understand? If here I had half of that, I would melt half the ice. If here I had 1/4 of that, I would melt 1/4 of the ice. Here I don't even melt 1/10 of the ice, because I don't even have 1/10 of the energy which I need to melt all the ice. I have like 8% maybe. We will compute that. Okay, so how much ice do we need? How much ice do we melt now? Let me continue the computation here. Okay, how much ice do we melt? We melt a quantity of ice which is equal to 21,200 joules, which is what we have, divided by 330,000, which is what it takes to melt all the ice. And if I do this division, I get 21,200 divided by 330,000. I get 0.064, etc. Okay, approximately. This I can express as a percentage. How much is it as a percentage? Hello. If I write this as a percentage, this is 6.4%. Could you not keep some mics open so that I have some feedback, some noise? Because yeah, thank you. Because otherwise I'm talking to a computer and I don't even know if you are still there. Okay, so we melt 6.4% of the ice. So we melt 6.4% of 1 kilogram. So it's 6.4% of 1,000 grams. So this is 64 grams. Okay, we melt 64 grams of ice out of 1 kilo. Okay, if you don't like this way of doing, you can also do it another way. You can say the energy which is available divided by the total energy is going to be equal to the mass of ice which is melted divided by the total mass of ice. Okay, so here this is 21,200. The total energy is 330,000. This is equal to the mass which is melted, which is what I'm trying to determine, divided by the total mass, which is 1 kilo. Okay, and so the mass which is melted, you can compute it as 21,200 divided by 330,000, but now your mass is in kilograms, okay? Because this is in kilograms, so this has to be in kilograms. It's no longer a percentage. The computation is the same. It's 0.064, but now it's 0.064 kilograms, and so it's 64 grams. So do it the way you want. It's going to be the same, okay? It's done a bit with the feet because doing it in a totally mathematical, clean way is a bit complicated. Okay, so we see what energy we have, what energy we need, how much is left, and voila. Okay. Okay. Do you want to work? Do you want to work? Because there's another exercise you could now do, and then we correct it together. I just have to be careful about the values because I know that in that course I did some mistake. So if you now take the other course, the one I just sent you, let's open it. Allez, move it. Oh God, sometimes it's so slow. Okay, so now if you go to the same page of the file, where is that? The exercise is here. You see that the C of acrylic glass, I confused the C with the specific mass. The C of acrylic glass is 1,450 joules per kilo per degree. And the C of Pyrex is not 2,320, it's 830, okay? And now it is an exercise where you have a mass, a glass of mass 200 grams. So your glass is 200 grams, okay, out of acrylic glass. Contains 2 deciliters, so 200 grams of water. Okay, the glass and the water are at the temperature of 20 degrees. They are in thermal equilibrium. And we put in this glass of water an ice cube of mass 20 grams. Okay, and the question at a temperature of minus 10 degrees. And what is the final temperature of the water? So you need to write down all the different terms. And of course, this ice cube is going to melt completely. So you have to include one term which accounts for heating up the ice from minus 10 to 0. And then one term for the energy it takes for the whole ice to melt. Okay? You want to try to do it? You want us to do it together? Let's do it together. Okay. So what are the terms that you need? Okay. You know that you have to get to an equilibrium equation, an equilibrium condition, which expresses the conservation of energy of this form. Okay. Now, we need to write a term for everybody. So the first term we could write is for the glass. Okay. The glass, it's acrylic glass, and the mass of the glass is 200 grams. Okay, so it's the mass of glass times the C of this type of glass, which is acrylic, times delta T of the glass. Okay, the mass of the glass, we said, is 200 grams, so in kilos it's 0.2. The C of the acrylic glass is 1,450. And the temperature difference, what is it? What is it? How do you write the temperature difference? What is the initial temperature of the glass? Hello, hello? Are you all dead or what? What is the initial temperature? 20. Okay, 20. And what is the final temperature of the glass? This is the equilibrium temperature. We don't know it yet. Oh, but sorry, you don't see my page. God, it's my fault. Ah, you should say, you should scream. I'm sorry. I'm sorry. So, the Q of we have the glass, the water, and the ice cube. Okay, I'm starting with the glass. The mass of the glass is 200 grams, so 0.2. The C of the glass is 1450, and the delta T is 20, final temperature. So it's initial final temperature TEQ, because we don't know it yet, we need to compute it, minus initial temperature 20. Okay, and we will have a similar term for the water, which is inside the glass. It's similar because we have the same quantity of water. So it's the mass of water times the C of water times the delta T for the water. The mass of glass of the water is 0.2. The C of the water is 4180, and the delta T is the same because the glass and the water which is inside are initially at the same temperature, and they will end up at the same equilibrium temperature, right? And now I have two more terms to write for the ice cube. Why two terms? Can you tell me why it's two terms and not just one? Why? The ice cube is at minus 10. Okay, so we need to heat it up. But once the ice cube has reached 0 degrees, it's going to melt. So we need another term to describe the melting of the ice. Okay, so the Q of the ice will be equal to a Q for heating it to 0 degrees plus a Q for melting the ice. Okay, there's somebody crying again. It's a little sister, I guess. Okay, so for heating up the ice, what do we do? It's the mass of ice times the C of ice. Be careful, it's the C of ice, not the C of water, times the temperature difference. And the temperature difference will be for going from minus 10 to 0. Okay, and then we have a second term here, which is the mass of ice times the latent heat for fusion, because this is the energy you will need to give the system to melt the ice. Okay, so let's compute these terms. Well, let's compute all of them, maybe. Okay, Q glass is what? Q glass is 0.2 times 1450 times Tec minus 20. Okay, the other term is 0.2 times 4180 times Tec minus 20. And then we have these two terms, for which I will put the numerical value. The mass of ice, this ice cube is what? 20 grams. Okay, so it's 0.02 kilograms. Don't forget to put it in kilograms. Times the C of the ice, which is 2050, times the temperature difference. What's the temperature difference now? Can somebody tell me what I should put in here? I'm trying to keep you alive a bit. What's the final temperature of the ice? It's going to 0. Okay? The final temperature of the ice is 0, and the initial temperature of the ice was minus 10 degrees. Okay? And now I have forgotten one term. What have I forgotten? I made a mistake until now. What have I forgotten in all that? Can you tell me? I forgot one term for the ice. Sorry? I have a term here which accounts for heating up the ice to 0 degrees. Then I have a term for melting the ice, but once the ice is melted, the water which is resulting from this melting is going to be at 0 degrees. So I still need a term which is mass of the ice times C of the water times Tx minus 0, because I am starting here with water at 0 temperature. I've just melted it, and this water needs energy to go up to the equilibrium temperature. But now it's no longer ice, it's water. So I need the C of the water, but the mass is still the mass of the ice, because this water that I have transformed, this ice that I have transformed into water had this mass initially. Okay? Are you following me? Yeah, so say something. Okay? So here we need the mass of the ice, which is again 0.02. Wait, where am I? Sorry. I was at this term, mass of the ice, C of ice, delta T. Okay, now let me write this term to be in the right, to follow the order, okay? This is the mass of the ice times the latent heat of fusion of water. The latent heat of fusion for water is 330,000 joules per kilogram. We saw it before. And then we have this last term, which I was about to forget, but unfortunately I didn't. This is the mass of the ice times the C of the water, because once it's melted, it's no longer ice, it's water, times Tx, which is my final temperature, minus 0, which is the temperature at which this former ice started to warm up. Okay? And all this should be 0. Okay? And now, well, we have a certain numbers of terms which multiply Tx, and a certain number of terms which don't depend on Tx. Okay? So all these terms, for instance, this times this does not depend on Tx. It comes with a minus sign. So I will put them on the other side, 0 to 1450, 20 with a positive sign. Okay? So this term is taken care of. This term is 0.2 times 4,180 times 20 with a minus, but I put it to the other side, it becomes a plus, so this term is taken care of. Now this term, okay, it's, you see, minus, minus, so the total of this is plus, the result is plus. Okay, so here it's going to be a minus because it's going to the other side, 0.02 times 2060 times 10. Okay? Are you still with me? Okay, so this term, all this has been taken care of because it doesn't depend on Tx. Then I have this term, but it's positive, so it's going to be negative on the other side, 0.02 times 330,000. Okay, this is taken care of. And then here we have 0, so we don't care for these terms, there's nothing, right? And now we take the denominator. The denominator is the sum of the factors of Tx, because we can write all these terms as Tx times something, so Tx will be this guy divided by the factors in front of Tx, so it's 0.2 times 1450 plus 0.2 times 4180 from here, so this is taken care of, this is taken care of. Here there is nothing depending on Tx, there is nothing depending on Tx, and here there is plus 0.02 times 4180. Okay, and now if I didn't do anything wrong, this should give us a result. So I'm going to try to compute that. If one of you wants to compute it too, do it. So this is 0,2 fois 1450 fois 20. This is 5,800. Then we have 0,2 times 4,180 times 20. No. 0,2 times 4,180 times 20. This is 16,720. Then we have 0.02 times 2060 times 10. This is 412. And then we have 0.02 times 330,000. Okay, and this gives us 6,600. Okay. Okay, the result is going to be positive. That's fine. And what do I have down here? I have 0.2 times 1,450, which is 290. I have 0.2 times 4,180, which is 836. And I have 0.02 times, so this is 83.6, right? Good. Now let's sum up all this. 5,800 plus 16,720 minus 412 minus 6,600. And so this gives us, I will write it down here, 15,508 divided by 290 plus 836 plus 83.6, and that's 1,209.6, and it's going to be wrong, I guess. No, it's not going to be wrong. 15,508 divided by 12,000 by 1,209.6. This gives me 12.82 degrees. Okay, do you believe it that an ice cube of 20 grams inside 200 grams of water at 20 degrees plus a glass, which also has to be cooled down, gives you a temperature difference of 7 degrees? It's pretty okay. We can try it if you want, but I don't want to go into my fridge, look for stuff. Okay, let's say the result is acceptable. All these terms here, what do they do? You see that this is terms corresponding to the cooling. I mean, it's corresponding to the initial energy contained in the glass, and this is the initial energy contained in the water. So this increases the equilibrium temperature. But the terms which are connected to what the ice needs to melt, okay, this is something which comes negatively, okay, because all this will make the temperature go down more because it's going to take energy from the system, same as the energy it takes here. So this is for heating up the ice cube, and this is for melting the ice cube. All this energy comes here with a minus sign, and so the more ice you have, the lower the temperature, the final temperature will be. Okay? Questions about that? No. Okay, so now we are done with this course and we should go to the next one. So what I will do today, I will not make it last until 5, don't worry, but I want to talk about one thing which is important, but there are no equations at all in the course. I'm just explaining that in French, because if you want to go into equations for that, it's going to take us way out of the program of the college. Okay, so this is just culture générale, let's say. Well, not only. We saw until now how heat is transferred between one thing and the other inside the system, but we never talked about which mechanisms heat uses to propagate. Okay, and this is the subject here. This is in the new course I send you. This is the way in which heat propagates, and heat propagates in 3 different ways. Exactly 3, which I am now going to discuss with you. Okay? So, One, one of these mechanisms for heat transmissions is the one which is working most often in solids. Okay, if you take a solid, let's say you take a bar of metal. Let's say you take a bar of copper. Why do I take copper? Copper, cuivre, okay? Why do I take copper? Because we know that copper is a very good transmitter of heat, okay? What does that mean? Well, if I heat up this copper here, if I put a source of heat, okay, this part of the copper is going to heat up, and then the heat is going to start being transmitted inside the copper until the other end is also warm. Of course, the other end will be less warm than this end because you have losses all along the copper. So unless the copper is perfectly isolated, you will have a higher temperature here than here. Who is doing mean things to his microphone? You should treat a microphone with some, you should treat your microphone with some more respect. Okay. Okay. So copper transmits heat, and all the solids, they transmit heat in the same way. How does that work? You know that heat, well, temperature, let's say, corresponds to the local thermal agitation of atoms. Okay. So here, when we heat up the substance with a flame, we heat up the copper atoms are going to vibrate more intensely around their equilibrium position. Okay, and so if they vibrate more, they're going to influence more the vibrations of their neighbors. Okay, so actually conduction, because this is the name we give to this mechanism, it's conduction of heat. Conduction of heat works at the atomic level, with every atom communicating to his neighbors this vibration energy. Okay, so if here it vibrates more, it will make the atoms here vibrate harder, etc., etc. And this state of increased vibration will progress inside the metal at a certain velocity, which is a few centimeters per second. Okay, if you do the experiment, you heat this up, you wait a few seconds, maybe a few minutes, and you will see the other end, which is heated up. And there is one experiment we do in class normally, but now I cannot do it. You take four pieces of metal. You take four pieces of metal, four different metals, or three or six, I mean, it doesn't matter. Okay, for instance, copper, iron, steel, and I don't know, brass. Okay, you put here in the middle a flame, and here at the end of these pieces of metal, you put a match, une allumette. Okay, with the side of the match which burns touching the metal. Okay, so this means when the metal has reached a sufficient temperature here, the match will start burning. Okay, and what you observe if you do this experiment is that the copper is the one that transmits heat faster. So after half a minute or a minute, you will see this match starting to burn, and then it's going to be the iron, then it's going to be the brass, etc. Okay, so different metals, they conduct heat at different velocities. But this mechanism works only in solids because it relies on the fact that neighboring atoms, which don't move, they transmit from one to the next this vibration state related to heat. Okay? In liquids, we have another mechanism which is very different, because in liquids, if you heat up a liquid, what happens? Let's take an example. You take a pan of water and you heat it up. So you put your flames down here, you heat the bottom of the pan. Okay, so the bottom of your pan will be at a certain temperature, maybe 200 degrees, maybe. Okay, But inside the pan, you have water. What do you think is going to happen if you heat up the bottom of the pan in physical terms? I know the water is going to get warm, but how? You don't know, you don't. Okay, you want me to say it. Okay, so here you have the bottom of your pan, which is at 200 degrees. Inside the pan, you have water, which is at maximum 100 degrees. Okay, at normal pressure, water boils at 100 degrees. So the water which is here in contact with the bottom of the pan is going to heat up first. But what happens if you have a substance which is heated up? Well, it's going to decrease its specific mass. When you heat up something, the specific mass decreases because the atoms, they are at a certain separation. Now, if you make these atoms vibrate harder, because you increase the temperature, since they vibrate harder, they will push each other away from the others, and so they will expand, they will take more volume. Okay, you know generally that when you heat up something, usually it goes up. Okay, we know in popular culture that warm air goes up and cold air goes down. This is true. Why is it? It's because warm air is lighter, has a smaller specific mass than cold air, so it goes up. It's the same for water. So what happens here is that this water, which has been heated up by contact with the bottom of the pan, it comes up. And also from popular culture, you know that everything that goes up must come down. So indeed, this water, when it comes up, it will lose its heat. It will give its heat to the rest of the water, which is still colder. And by losing its heat, it will gain again a higher specific mass, and it will go down again. Okay, so inside a pan of water which is heating up, not when it is boiling, but because when it is boiling, you have all the balls going up, and this nice structure is destroyed. But when water is warming up, you have formation inside the water of these kind of rolls. Okay, if you look at the pan from above, it's going to be something which goes like this. Okay, from the center to the sides. And by the way, this structure has a name. It's called rouleau de Bénard. Bénard must be the guy who discovered that. Okay, and this happens in any fluid that you warm up. This, of course, doesn't happen for solid, because inside solids matter doesn't move, but inside liquids matter moves. Okay, and so inside liquids we have this mechanism of heat transfer, which we call convection. Okay. By the way, maybe you bought a radiator sometime, an electric radiator, and you saw that it was named convecteur. Un convecteur électrique is another name for a radiateur. What is a convecteur électrique? Now let's imagine your bedroom. Okay, don't worry, I will not come make pictures of your bedroom. Let's imagine your bedroom. Let's say that this is the wall of your bedroom. Okay, and let's say that here inside your bedroom you have a radiator from your central heating system. Okay, and let's say that here there is your bed and everything. Okay, good. And here we have a window. Isn't that beautiful? Okay, what happens inside your room? Why is your room warm when the central heating is working? The central heating is here. How can it warm up all the room? It's exactly the same mechanism. It's by convection, because the radiator warms up the air which is in contact with it. So it warms up the air inside this volume here. Okay, but the air which is warm, now it goes up because its specific mass is lower. Okay, This air goes up and as usual, everything that goes up must come down. So the air is going to now go somewhere inside the room. It's going to come down somewhere inside the room. And in that way, there will be a circulation of air inside the room, which is going up above the radiator, which is coming down inside the whole room, and then it's going to, and then on the floor you have the cold air, and this cold air will be progressively heated up again by the radiator, will go up again, etc., etc. Are you still with me? Hello? Isn't that fascinating? Okay, so this is why when you look, if your house has not been repainted recently, you see there is always some dirt on the wall above the radiator. And this dirt on the wall, it's like, it's a uniform dirt, it's a bit gray. Okay, this is what? This is just a deposit of poussière. How do you say poussière? A deposit of oh God, how do you say poussière in English? I have a of dust. Okay, this is a deposit of dust which sticks on the wall because this dust is carried up by the warm air which is going up. So it's always dirty above the radiators because of that phenomenon. And even if you keep your house very well, this is not going to go away. If you want to get rid of that, you have to repaint. Okay? Okay, so we have, I discussed two mechanisms, one in solids, conduction, one in liquids, convection. Okay? But now you know very well that the sun, for instance, is sending us heat. The sun is warming Earth. Okay? Without the sun, we couldn't live. Without the sun, the Earth would be at minus 260 something degrees. Life would be inexistent. Well, no, it would maybe be a bit warmer because inside Earth there is a heat source. But it would be very cold. We could not live here. So, how does the sun send us heat? It cannot be through conduction because between the sun and us there is the vacuum of space. So it's impossible that heat arrives with this mechanism. Can it be convection? Well, there is no air between the sun and the earth, so the heat cannot be transferred to us by movement of some gas. There has to be a mechanism for heat transfer which works in vacuum. And indeed it exists. And this mechanism, it's called radiation. Rayonnement en français, ou radiation. Okay? Radiation is what? You have the sun here, and here you have the earth. Okay? The sun is sending rays of light and other stuff. Okay? There is light, but there is also infrared waves. There is also ultraviolets, there are radio waves, there are all kinds of stuff which is coming from the sun to us. And these are electromagnetic waves. Okay, you will learn about electromagnetic waves in the third year, but I can already tell you an electromagnetic wave is a combination of an electric and a magnetic field that can travel through space. Even if space is empty, it can travel through emptiness, through vacuum, because the electromagnetic waves, they are a combination of an electric field and of a magnetic field, which oscillate on two perpendicular planes. Okay, and so the variation of one field causes the appearance of the other field and vice versa. So these vibrations of the magnetic field and of the electric field, they auto-entertain each other, and so the wave can travel through the vacuum and arrive on Earth and bring us heat, because these waves, they don't carry matter, but they carry energy. Okay? Voila, that's the three mechanisms. And now you see here an illustration of that, two illustrations. Here you have a fire, a wood fire, okay? If you put your hands next to the fire on the side, It's not the heat of the fire which is coming to your hand through the air. No. Here, what you feel on your hands when you put your hands towards the fire is the radiation, because the radiation does not happen only in space, it happens also in air. This is infrared radiation which hits your hands and warms up your hands, and you can burn yourself with that. It's pretty strong. Okay. Now, if you put your hands above the fire, of course you will also have radiation, but here you will also have convection. You will have this air which has been warmed by the fire, which is now going up because its specific mass is lower. And if you touch your fire with a piece of iron, the piece of iron will become warm and you can burn yourself with that. But that's through conduction of the heat inside the iron. Okay? I don't know if you're still there. I feel very bad now. And now another example. You have a fire with you are heating up water inside a pan. You see that inside the pan, the heat which is given to the water at the bottom of the pan is distributed inside the pan by convection movements. Okay, you see that conduction can lead to you burning your hand with the handle of the pan. This is why the handle of the pan should never be a good heat conductor. This is why the handle of a pan is often made out of plastic or of wood, okay, because wood is a very good heat insulator. And you have this radiation coming out from the fire and heating whatever is next to it. Okay? Are you still there? Oh my God. Yes, you are still there. Okay. So next week, what we're going to do is to look at dilations of solids, gases, and liquids. And then we are going to look at something which is quite important, which is the ideal gas law. Okay, maybe you saw this law already, PV equals nRT, because in a gas there is always a relationship between the pressure, the volume, and the temperature. So we're going to look a bit more into that, and that will be it. Okay? You've been so silent, my God. Okay, I will put the video online, and please for next week print the end of the course that I sent you today on Classroom. Okay? Okay. Bye-bye. Bye-bye. Bye.